Hello, I'm Patty Simpson with Simpson Math. In this video, we're going to look at the domain from the equations of various functions. In a previous video, we looked at the 7 functions that we've graphed, and we saw that only 2 of those functions had any restrictions on the domain. The 2 that had restrictions were our rational functions and our square root functions. For the rest of our functions, the domain was just all real numbers. We could put in any value for x and get out a real value for y. So let's look at these equations. This first one is a cubic function. I know because the degree of that function is 3. So this is a cubic function. Cubic function is not one of the ones with a restriction. So the domain of our cubic functions is just x can be any old real number. In set builder notation, x such that x is an element of the real number, or in interval notation, x can be anything from negative infinity to positive infinity. Here, this is a rational function. My x is in the denominator. That's one of the ones with the restriction. The denominator here cannot be equal to 0. So therefore, we just take our denominator and we set it not equal to 0 and we solve. So subtract 7 from both sides, and x cannot be equal to negative 7. If I put negative 7 in here, I get 0 on the bottom. So my domain here, my x value can be anything, any real number. It just cannot be negative 7. Or in interval notation, my domain can go from negative infinity to positive infinity. It just has a problem in negative 7. So we're going to jump over negative 7. Negative 7 is not going to be included. So we're going to have a graph from negative infinity to negative 7. And then we're going to have another part of the graph from negative 7 to infinity. Negative 7 is just not included in there. So that's the domain for that rational function. Here, this is a square root function. Our square root functions also have a restriction on the domain. Underneath the radical has to be positive. So must be greater than or equal to 0. So we take what's underneath the radical and we just set it greater than or equal to 0. We can't have a negative underneath there and get out a real value. Then we solve. Add 20 to both sides. So we have 5x is greater than or equal to 20. Divide both sides by 5, so we have x must be greater than or equal to 4. If I put 4 in here, 4 times 5 is 20, 20 minus 20 is 0. If I put in anything smaller than 4, I'm going to get a negative number. So to write my domain, my x values must be greater than or equal to 4. To write it in set builder notation, I say that x has to be greater than or equal to 4. In interval notation, the smallest number it can be is 4, and it is included. That equal sign tells me it is included, and it has to be bigger, so it goes all the way to infinity. Here, this is an absolute value function. That's not one of the ones with the restriction, so therefore my domain is all real numbers. For all of my absolute value functions, my domain is all real numbers. Here, I have a rational function. Again, my denominator cannot be equal to 0. So I'm just going to take my denominator. Notice I'm not worried about the numerator. I'm only worried about the denominator. And I'm going to say it cannot be equal to 0. And then I'm just going to solve it. Well, here I have, it's already set equal to 0, so I'm going to factor, my favorite F word. This is a difference of squares. So I'm going to factor him using the difference of squares and x in the front. The square root of 25 is 5. And I know with my difference of squares that my signs will be opposite of one another. Now I have 2 numbers that are multiplying together to equal 0. Either that first one is equal to 0 or the second one is. Then I solve, subtract 5 from both sides. Add 5 to both sides. So my x cannot be 5, and it cannot be, I subtract 5 from both sides. It cannot be negative 5. So my x cannot be negative 5, and it cannot be 5. It can be anything else. It can be any other real number, just not negative 5 or 5. So in set builder notation, we say x such that x is an element of the real number, but x cannot be -5 or 5. In interval notation, I go from negative infinity all the way to positive infinity, but there's a problem at -5, so I'm going to stop at -5, jump over that -5, then I'm going to go to 5, jump over the 5, and then go to infinity. So this says I can go from negative infinity to infinity. There's just a problem there. It can't be -5 and it can't be 5. Here I have another rational function. In this case, I have two denominators. Neither one of them can be equal to 0. So I'm going to take my first one and say it cannot be equal to 0. And I'm going to take my second one and say it cannot be equal to 0. I'm going to solve for both, add 4 to both sides, subtract 6 from both sides. X can be any value. I can input any other value. I just cannot input 4 and I cannot input -6 and get out a real number. If I put in 4 or 6, it will be undefined. So my domain here in set builder notation, X can be anything. It just cannot be -6 or 4. And in that interval, this is set builder, in interval notation, I can go from negative infinity to positive infinity. I just have an interruption in the graph at -6. And then from -6 to 4, there's a piece of the graph there. Then from 4 to infinity. So in other words, it goes from negative infinity to infinity. There's just a break in the graph at -6, and there's a break in the graph at 4. But otherwise, every value is covered in there. So set builder notation and interval notation. Here, I have a square root function. Square root functions do have a restriction. Underneath the radical cannot be negative. So I'm just going to take this underneath the radical and set it greater than or equal to 0, and I'm going to solve it. So maybe we solve here by adding 11x to both sides, so that we end up with 22 is greater than or equal to 11x. Divide both sides by 11, and you have x is less than or equal to 2. Or you could turn that around and make it x is less than or equal to 2. These two things are the same thing. In set builder notation, x such that x is less than or equal to 2. In interval notation, notice that it's less than 2. So 2 is the biggest number I'm going to have, and then it goes to negative infinity. It's anything smaller than that. So in set builder notation, but in interval notation. Here I have a rational function. Now this rational function actually has two denominators. There's a denominator here in this function, in this part of the function, 8 over x. Then there's a denominator here for this fraction. So there's a denominator here and a denominator there. Both of those denominators must be not equal to 0. So I'm going to take this little denominator, and I'm going to say it cannot equal 0. And then I'm going to take this big denominator, and I'm going to say it also cannot equal 0. So both of those denominators cannot equal 0. This one's already solved. We solve here, add 1 to both sides. So that I have 8x equals 1. Multiply both sides by x, and I get 8 equals x, or not equals to x. So in this case, if I put 0 in there, then it's undefined. If I put 8 in there, 8 divided by 8 is 1. 1 minus 1 makes that denominator 0. And therefore, it would be undefined. So again, in this function, my x values can be anything else. They just cannot be 0, nor can they be 8. So like these others in interval notation, I'm going to go from negative infinity out to positive infinity. I just have an issue at 0, a break in the graph at 0, and a break in the graph at 8. So we go from negative infinity to 0, union that with 0 to 8, union that with 8 to infinity. So for all of my functions, if there are only two that have the restriction. The restrictions are the square root function, in which case we take the radicand and say it has to be greater than or equal to 0, or the rational function is the other one with a restriction, and in that case we take the denominator and say it cannot be equal to 0. So those are the domains for my equations. Math made simple at Simpson Math. Thanks for watching.